You know, it's commonly understood that any actor or actress in Hollywood can be linked back to me, Hollywood legend Kevin Bacon, in 6 steps or less. But is it true? Let's test that theory. Let's start with an oldie but a goodie, Mr. Marlon Brando. Brando was in The Godfather with Diane Keaton. Diane Keaton was in Annie Hall with Christopher Walken. Christopher Walken was in Catch Me If You Can with Tom Hanks. Tom Hanks was in Apollo 13 with Hollywood legend Kevin Bacon.
So, the Kevin Bacon game, also known as 6 Degrees of Kevin Bacon. I'm sure you've heard of it. Maybe you've never played it. Today we're going to talk about how you might be able to optimally play this game if you had a database of all Hollywood actors and what screenplays they've been in. Let's say the IMDb database. How could you compute the shortest distance between any Hollywood actor and Kevin Bacon? Let's take a look at that now. So this brings us to breadth first search. Remember that we've been talking about depth first search. I mentioned breadth first search very briefly in a previous video. Depth first search is good for connectivity, finding connected components in an undirected graph. It can be used for topologically sorting a DAG. If you remember, you just sort by decreasing post number after you've run DFS with pre and post numbers. It can also be good for finding strongly connected components of a general directed graph. Today we're going to look at breadth first search, and this is good for finding distances in graphs. BFS is good for computing the distance between 2 nodes in a graph. What's interesting is the only difference between BFS and DFS is that DFS uses a stack when it finds new nodes. It adds new nodes to a stack. A stack uses the LIFO, last in first out method of taking items off of this data structure. But BFS uses a queue. A queue uses FIFO, first in, first out. So let's take a look at an example of DFS and BFS being used to search through a graph. So here we have a graph on the left. Let's think about how we might search through this graph, starting with some root node S. In DFS, depth first search, S first goes to its first neighbor A then looks at its first neighbor B then looks at its first neighbor C, sees that it's discovered S, so it returns back to B has no more unseen neighbors, A has no more unseen neighbors, S finds that it has an unseen neighbor D, we then go to D's neighbor E has no more unseen neighbors, and we pop back up to D, back up to S, and then we're done. So it produced this little search tree right here, right? First S went to A, then A found B, then B found C. Notice that it required this long chain to get down to C. Okay, so what happens in breadth first search? In breadth first search, you start with a root node, and you add all of S's neighbors to a queue. So first you would just take node A, node C, node D, and node E, and add them to the queue in some order, let's say in that particular order. You first explore A. You notice that A has an unseen neighbor B. You would add B to the queue, but your next exploration node would actually be C. You then explore C. C has no unexplored neighbors other than B. That's already been explored. You then explore D. You would add E to the queue, but actually E has already been added to the queue. You then continue to E because E is S's last unobserved neighbor, unvisited neighbor. Then the only remaining item that's in the queue is B. You then finally explore B. B has no unexplored neighbors, so you're done. What you'll notice is that breadth first search first found all of the nodes that were directly connected to S, and then only later found the nodes that were 2 hops away from S. In that case, that's just node B. So you'll notice that it found all of these closest nodes first, and then it moved on to the nodes that are degree 2 away from S, and so on. And this is a nice feature of BFS. It actually finds nodes in the order of how close they are to the root node. So let's actually see some code in action to see how this actually works. Okay, so here's some pseudocode. I guess it's working Python code that's going to use breadth first search to compute distances from some root node, let's say v of 0. So this function, well, first of all, let's note that it uses this queue data structure, which is built into Python. We're gonna use this queue in a moment. It takes in a graph, which is a vertex set and an edge set. It initializes some initial dict to be empty. It pulls off a root node, which you're going to call root. It's v of 0. It's the first vertex in the list. It initially sets the distances from for all nodes v in the vertex set to be infinity. Just sets them to be infinite. It will initialize the distance between, what this distance is doing is measuring the distance from to v from this root. So actually you're going to initialize dist of root to be 0 because the distance from root to itself is going to be 0. It creates this new queue and it puts the root node inside of the queue to be explored. So here's how this algorithm works, what the loop is doing. It's going to look at the queue. It's going to say, are there any elements left in the queue? And if there are still some elements left in the queue, it's going to take that node out. For every neighbor listed in this, node's edge set, it's going to check to see if the distance is infinity, which means you haven't actually seen this neighbor yet. It's going to put that neighbor into the queue. And it's going to set the distance from neighbor to root to be the distance from this node plus 1. It's going to say that the distance from root to the neighbor is going to be the distance to the current node plus 1 because it required one extra hop to get to this neighbor through the node. And the running time of this algorithm is going to be on the order of n plus m. You'll see that essentially you have to do a loop through the vertex set once. That's an O of n operation, and you're going to have to look at every single edge in the edge set and do this O of 1 operation. And in total, this whole thing is going to be on the order of n plus m. There's only one small issue with the method we've seen so far. Well, it's limited, basically. You'll notice that was an unweighted graph. There weren't any numbers associated with the edges. In typical cases where we want to compute distances between things, we often have these weights associated with every edge. Getting from Sacramento to Reno, let's say, is 133 miles, and getting from Reno to Las Vegas is 445 miles. We'd like to take into account these costs on the edges to minimize routes, let's say, to Bakersfield. If you want to get to Bakersfield, or let's say Reno from any other city, we want to find the shortest distance on the roads through highways, the roads and highways have number of miles associated with them, and we like to take advantage of that. So how do we do that? Here's a simple trick you might try to take advantage of the weighted graph when you have edge weights. You could simply take your edge weights, assuming that they're integer values, let's say positive integers. You could take the weight on every edge, here you have an edge with weight 2, and just turn it into two edges by adding this dummy node. You have this extra node here. A connects to the dummy node, and then the dummy node connects to B. When you have a weight of 4, you have to use 4 dummy nodes. C connects to dummy node 1, dummy node 2, then dummy node 3, then E, right? And this would be one way of trying to convert your weighted graph into an unweighted graph, and then we can use BFS, compute distance, on this particular graph, which is much larger. This is an okay idea. It will work in finding shortest distances using breadth first search. The problem is it's not very efficient, right? We're kind of making this graph potentially much larger and making a much more expensive algorithm in order to compute distances. We'd like a smarter way to do this, and we also may want to have to incorporate real numbers, not integers, right? We could have 4.5 as a weight on one of these edges. And we'd like to be able to do this for arbitrary positive real numbers and finding shortest distances in graphs with arbitrary weights on them, arbitrary positive weights on them. So we're going to focus on that in the next video, and we're going to learn about how do you do Dijkstra's algorithm.